This is your lesson on radical operations, and it's going to cover the sections 5.5 and 5.6 from Glencoe. As you can see, it's going to address a lot of learning targets, so it's very important that you're taking notes throughout the video as well as throughout reading the chapter. All right, I'm first going to talk about example 1, where there are 4 examples, and I'm asked to find the roots of each of the scenarios. All right, let's begin. So looking at option A, problem A, we have plus or minus the square root of 25x to the 4th. So this is probably going to sound familiar from Algebra 1. The plus or minus here is just part of our final answer. It's just saying that whatever we produce, it could be positive or it could be negative. First off, we're going to look at the square root of 25. As we all know, the square root of 25, my personal favorite radical, is going to be 5. The next part of the square root that I'm looking at is x to the 4th. You can see me as I'm illustrating this example that I'm using the product property where I'm breaking these into separate radicals. The square root of x to the 4th, well, that's really the same as me saying x squared times x squared, which is why the square root of x to the 4th is x squared, because both of these terms are now appearing twice, and I can pull one from outside of the radical. When we're looking at B, notice that we have a negative, and he is going to be part of our final answer. We're just going to have a negative quantity. When I have the square root of a quantity to the 8th power, one way of looking at it is the fact that I'm going to have this y squared plus 2 squared multiplied by itself again, y plus 2 squared, and so forth, okay? I'm really going to have that quantity appear once, twice, 3 times, and 4 times, okay? And because I have that quantity, that perfect square quantity appear 4 times, I can now pull out the quantity y squared plus 2 to the 4th power, okay? Your textbook just simply rewrites this as being raised to the square power. I highly recommend looking at that. When we're looking at C, all of a sudden, we're dealing with a 5th root. The index is 5. That means things need to appear 5 times in order to be pulled out of a 5th root. All right, so the first part I'm going to look at is what the 5th root of 32 is, okay? Well, 32, that's really just actually going to be 2 to the 5th power. So the 5th root of 2 to the 5th power is just going to produce 2. Now I'm going to look at the 5th root of x to the 15th, okay? Well, what that term really is going to look like is the 5th root, and one way of seeing it is as the quantity x to the 3rd to the 5th power, which is why the 5th root of x to the 15th is just going to leave us with this quantity x to the 3rd, okay? So now we're dealing with the 5th root of y to the 20th. Well, that can just be rewritten as the 5th root of the quantity y to the 4th to the 5th power, leaving us with y to the 4th on the outside of the radical. D, however, is the square root of negative 9, and there is no real solution here. Now, you probably will recall that we are dealing with imaginary numbers here, but in this chapter, in this unit, we're going to be focusing on real solutions. We're going to finish up this section with 2 more examples. In example 2, we're going to be simplifying radicals that are going to involve a final answer involving absolute value. Now, absolute value can occur in your final answer when you're doing an even index and it produces an odd degree, okay? So the 8th root of x to the 8th, that simplified is just going to produce x to the 1st power, okay? Now, one of the keys is the fact that we were dealing with an 8th root. That's an even index. The second key is the fact that it produced an odd degree, which is why I need to produce absolute value bars around the x. The reason we have to do this is let's pretend let x equal negative 2. If we had the 8th root of x to the 8th and we're plugging in negative 2 to this quantity, negative 2 to the 8th power is going to produce a positive answer. However, this was supposed to be equal to x, which was equal to negative 2. That would never produce a negative answer, which is why we need to give absolute value bars to our final answer. All right, looking at B, we have the 4th root of 81 times the quantity of a plus 1 to the 12th. Let's break it up into two problems. The fourth root of 81 times the fourth root of the quantity a plus 1 to the 12th. When dealing with the fourth root of 81, well, 81 can really be represented as 3 to the fourth power. The fourth root of 3 to the fourth power is 3. I don't need to worry about absolute value bars here because 3 is a constant. He is what he is not a negative. The fourth root of this quantity, well, I can take this quantity of a plus 1 to the 12th, and I'm going to rewrite this as a plus 1 to the third being raised to the fourth power. Okay? Another way of doing this is just simply rewriting a couple quantities to the fourth power, a plus 1 to the fourth times a plus 1 to the fourth times a plus 1 to the fourth, so that you'd eventually start to see the fact that you can pull 3 of those quantities out. Because I can pull 3 of those quantities out, it produced an odd degree from an even index. This is the scenario where I need to give my absolute value bars to this quantity of a plus 1 to the third. All right, we're looking at a real-world problem now where I'm approximating a square root. We're given a formula, t equals 2 pi times the square root of L over g. And we are told to find the value of t when given a 30-foot long pendulum. So we're really just going to plug in numbers here. So t is going to be equal to 2 times pi, then we have the square root. So L is going to be the length. Our length is going to be 30. And I just realized that I mistyped that in your notes. Make sure that you notice that in the textbook, it actually says that the length is going to be a length of 3, which would make a huge difference for us, okay? So let me cross that off here because it won't let me erase. So we have 3 over 32, where 32 is this gravity component right here. All right, so all we need to do is type this into our calculator here to approximate this. Now be very cautious as to how you're typing it in. I want you to actually type it in to make sure you end up getting the exact same answer as the textbook, okay? When you type this in, you're going to get a decimal. If we're going to round, let's round to 2 decimal places, okay? You should get approximately 1.92, so in the context of this real-world problem, our unit is going to be seconds. All right, we're now in 5-6, example 1, but now we're going to start off by simplifying another square root. All right, let's use the product property and separate these. We really need the square root of 16, the square root of p to the 8th, and we're also really dealing with the square root of q to the 7th. Well, the square root of 16 is 4, and now we're looking at the square root of p to the 8th, okay? Well, one way of looking at it, if you're more visual and the properties of exponents aren't working for you, is think of it. It's just p squared times p squared times p squared times p squared. The square root of p squared, that's going to give me a p. So is this guy, and this guy, which is why it's going to produce p to the 4th. Now q to the 7th, we can rewrite that as q squared, q squared, q squared, and another q. And so these 3 guys can come on out, but he needs to stay underneath the square root. So we have 3 q's coming out. That's why we get q to the 3rd. And we're going to multiply this all by the square root of q. Okay. Now, the one thing we do need to worry about are those absolute value bars. Notice the 4 is what the 4 is. The p is now to the 4th power, so that's an even degree. But the q to the 3rd is an odd degree, and it was taken by the square root, which is an even index. Okay. All right, so now scrolling on down. Let's look at example 2 where we're simplifying quotients. When simplifying quotients, we can separate things into 2 separate radicals because there's division happening. So this is really going to be the square root of x to the 4th over the square root of y to the 5th. If we start simplifying these, then we will rationalize this. The square root of x to the 4th, that's going to get me x squared. Now, the square root of y to the 5th, that's really going to be y squared, y squared, y, which is why it's going to be y squared times square root of y. Now, radicals are not allowed in your denominator, so we must rationalize this. So I'm going to multiply both the top and the bottom by a square root of y, okay? The reason I'm doing this is because when I multiply radical y by radical y, that's going to get me the square root of y squared. And that's going to be a perfect radical, giving me just a y. That way I don't have a radical in the bottom, okay? So let's actually multiply these out. So on the top, we end up with x squared times square root of y. On the bottom, we end up with y squared times square root of y squared. And so then, the top is as simple as it gets. We can't simplify it any further. But on the bottom, we're going to produce a y from this guy. So y squared times y gets me y to the third. Okay? Now let's take a look at b. Let's give our own space here. Now b is the fifth root. So the fifth root's a little bit more complicated, okay? So let's break it up. We have the fifth root of 5 on the top, and on the bottom we have the fifth root of 4a, okay? So, to figure out what we need to multiply both the top and the bottom by, I always like to explain it as, think about the goal, the end in mind. So we have the fifth root, okay? Let's start with the a's. Right now we have a to the first. We want to end up with a to the fifth. So, let's see. We have to have a fifth root because we need to be able to multiply underneath the radical. If we have 1 and we want 5, we need to multiply by 4 more a's, so a to the fourth. So far we're going to multiply by the fifth root of a to the fourth. Okay, now what about that 4? Another way to interpret the 4 is he's really just 2 squared, where I have 2 2's. I want to have 5 2's. That way I have a perfect fifth root in my denominator. So if I have 2 2's and I want 5 of them, I need to multiply by 3 more 2's, or 2 to the third. Okay? So let's actually multiply this on out. The denominator here is going to produce the fifth root of a to the fifth and 2 to the fifth. Okay? That's why I'm going to have a nice perfect fifth root on the bottom, which just gives me 2a. Okay? Now the top is a little bit more messy. Okay? 2 to the third, that's really 8. So it's going to leave me with the fifth root of, well, 5 times 8 is 40, a to the fourth. Now this can't be simplified anymore. It is something for you to check on. But this is going to be our final simplified answer. On to example 3, where we're starting to multiply radicals. All right, so here I have this expression 6 times the cube root of 9n squared multiplied by 3 times the cube root of 24n. When multiplying radicals, when multiplying on the insides, it's important that you have the same index, okay? Notice these are both 3's, okay? So first off, I'm going to multiply the outside numbers. 6 times 3. Well, that's going to get me an outside coefficient of 18. Now look into the inside here. Something that might be helpful is breaking down what the numbers are that you've been given. Well, 9, that's going to be 3 times 3, okay? 24, well, 24, that's going to be 3 times 8. Now, 8 we can also break down to 4 times 2. But 4, we could break that down even more. Goodness. 4 times 2, that could be broken down to 2 times 2 times 2. Let's double check our work. 3 times 3, that was 9. And then we have 3 times 2, which is 6, times 2 is 12, times 2 is 24. All right, we're still good. Now the first radical gave us an n squared, and the second one gave us an n. Well, that's going to be n to the third. All right, see what we can do. So 3 3's means I can pull 1 out. 3 2's means I can pull 1 out. This is going to give me 3 n's, which means I can pull 1 out. So I pull out one of my 3's, I pull out one of my 2's, and I pull out one of my 1's. So we have 18 times 2 times 3, getting me 108 n. All right, now let's look into adding and subtracting radicals. It's important when adding and subtracting radicals that you get the same radicand underneath the same index. So notice all 3 of these terms have not been simplified, so I first need to simplify each of them. 2 radical 12, well, square root of 12, that's really 4 times 3. And the square root of 4 is 2, so I pull that outside. So we have 2 times 2 radical 3. So that term's really just 4 radical 3. Now, let's take a look at 3 radical 27. Well, square root of 27, that's just going to be 9 times 3. And the square root of 9, that lets me pull out a 3. Leaving this term to really be 3 times 3, which is 9, radical 3. Last term, let's take a look at him. We have a 2 square root of 48. Ooh, 48, that's a little bit more difficult, okay? But that's really going to be 16 times 3. And the square root of 16 lets me pull out a 4, radical 3. And 2 times 4 is 8, so he's really 8 radical 3. Wow, look, all of them now have the same radicand. So now what I must do is all I need to do is look at their coefficients and add their coefficients, okay? One way of looking at this is it's really 4x minus 9x plus 8x, where x is just equal to radical 3. Did that make sense? All right, so when I add them together, 4 minus 9 is negative 5. Negative 5 plus 8, that's going to be 3. Notice I did not touch the radicand. He remained the same. Now let's multiply some radical expressions here. So notice that in both of these examples, I have two binomials, so all I need to worry about is FOILing. So it's just me a couple multiplication problems happening at once. 3 radical 5 times 2 gets me 6 radical 5. 3 radical 5 times radical 3, well, that's going to get me 3 times the square root of 15. All right, now let's take a look at 2 radical 3 times 2. That gets me negative 4 radical 3. Then we have negative 2 radical 3 times the square root of 3. Now, radical 3 times 3, that's just going to get me 3, which is why this last term ends up being negative 6. Notice that when we multiplied all these out, even though they look like they could contain some of the same things in their radicand, none of them simplified anything more than what I have circled here, okay? It is what it is. Let's look at B. B is an example where we're multiplying the conjugates. 5 radical 3 minus 6 times 5 radical 3 plus 6. So if you recall, that's the situations of having a difference of squares, which you should hopefully also remember. That means it's a quantity squared minus a quantity squared. So my A term is really 5 radical 3, and my B term is really 6. So all I really need to do is simplify this expression. Well, 5 radical 3, that quantity squared, is going to get me 25 times, well, the square root of 3 squared is just 3. So we really have 75 minus 36, and 75 minus 36 is 39. Look at how much easier that was. Did you notice how in the last example we ended up with just a constant term and no radicals? We're going to use this same logic to eliminate a radical expression from our denominator, because you're not allowed to have radicals in your denominator. Now, it's important to remember, whatever we're going to multiply this guy by, it can only ever equal 1, okay? Because that does not change what the expression means itself. Notice that before, all we had to need to do was multiply by the conjugate in order to get rid of the radical. But what you do to the top, you must also do to the bottom, okay? Likewise, the bottom to the top. So on the bottom, it produced a difference of squares. So that'll be quick and easy and pain-free. On the bottom, it just produces 25 minus, well, the square root of 3 squared is 3. So it's going to be 25 minus 3, which is 22. But on the top, we need to FOIL out our expression. So I'm just going to give myself some extra room down here. So we have 1 times 5, which is 5. 1 times negative radical 3, which is going to be negative radical 3. Negative radical 3 times 5 is negative 5 radical 3. And a negative times a negative is a positive, and we end up with positive 3. 5 and 3 are like terms, and oh, look at that. These two guys are also like terms. So on the top, we end up with 5 plus 3 is 8. And then negative radical 3 and negative 5 radical 3 is negative 6 radical 3. And this is all over 22. Now I can actually take this a step further because a number that goes into all of these terms, 8 6, and 22 is the number 2. So I'm going to divide everything by 2 so I can simplify this expression. And I end up with 4 minus 3 times radical 3 over 11.